In this video, we're going to look at the 2's complement notation, and I'm going to show you one method of how to do this notation. In a further video, I'm going to show you a different method of using the same notation. So, why do we actually need the 2's complement notation? Don't we have everything that we need in the binary numbers that we already learned about? Well, actually, we haven't talked about the negative numbers in binary yet. Obviously, in decimal numbers, when you want to talk about negative numbers, all you can do, put a negative sign in front of any numbers, let's say 3, and then you know that this is a negative number. Now, when it comes to binary numbers, how are we going to put a negative sign in front of these zeros and ones? And don't forget, these zeros and ones are to be used with the computer. So obviously, when you look at a negative sign in front of a long binary sequence, then you can see that this is negative, but it's not good enough for the computer. So people were thinking about, okay, how we can come up with a negative number in binary. And the idea is following. Well, we've got two different digits, 0 and 1. So what about if we say 0 is a positive number and 1 will be a negative number? So the point of the 2's complement notation is that when you're looking at the notation, if the first digit is 0, then you know that this is a positive number. And if the first digit is 1, then you know that this is a negative number. So, how does the actual conversion works? First of all, we need to agree a fixed length for these binary numbers. Because if we just have got any odd lengths, then the computer will not know what digit is the first digit, what digit will be the sign digit. So we can talk about 4 bits 2's complement. We can even talk about 6 bits 2's complement, and so on. It doesn't have to be an even number, it can be 7 bits 2's complement as well. So the first thing that you need to agree with is how long your bit sequence is, how long is the binary number that we're talking about. Once you fix the length of binary number, then the first digit will be used for the sign. Therefore, straight away introducing a limitation to how many different numbers you can represent in that specific sequence. And the steps then follow. So step 1 will be convert into binary. Step 2 will be, and this is probably going to sound a little bit confusing, but when it comes to showing it, you will see that it's actually not too difficult. So copy the digits until you copied 1. Then you invert, and by invert I mean you change the 0 into 1 and the 1 into 0, all the digits. One thing that you need to be aware of is that when you're copying the digits, you are copying it from the right hand side and you're moving towards the left hand side. Now, enough of the talk, let's see some examples in action. So let's say that you wanted to convert -5 into a binary using 4 bits 2's complement. Now, because we're talking about 4 bits 2's complement, then every single number in this binary system have to be 4 bits long. Now, that's very, very important for any complement system, that the fixed length is always the same for all of the numbers. So, let's say we talk about 0, so then 0 would be, in this 4 bits 2's complement notation, 4 zeros. Not just 1 0, 4 zeros. Then 1 would be 3 zeros and a 1. So it's really, really important that the bit length you keep fixed. So then what was step 1? Step 1 was conversion. So how do we convert 5 forget about the negative sign for a moment. How do we convert 5 into binary? Well, we remember that we have got the binary place values 1, 2, 4, 8, and don't forget we've got only 4 bits, so that's all the bits that we can use. Which one of these we need to use to build up 5? Well, 5 is just the sum of 4 and 1, so the other 2 are zeros. And remember, it's 4 bits, so I need the first 0 in here. This is not an unnecessary or 0 anymore, this is a necessary 0 now, otherwise we reduce the number into 3 bits. Okay, so that was the first step, wasn't too painful. Then step 2 was the inversion. Now this inversion was a little bit complicated. What I said is copy the number until you copied 1. So we start to copy the number from the right side, which is the smallest place value. But look what happened. I copied, the first digit I copied is a 1. So I've already copied a 1. So what I need to do then, I need to invert everything else. So I copied the 1, the 0's inverse is 1, the 1's inverse is 0, and the 0's inverse is 1. So -5 in decimal looks like 1011 in 4 bits 2's complement notation. The next example is -7. Let's just stick with the 4 bits 2's complement again. Again, every single binary number in this system is 4 bits long. So when I want to convert -7, the first thing is I look at the positive equivalent, the 7, and I convert that into binary. So that will be step 1, conversion. So again, use the binary place value 1, 2, 4, 8. I've got 4 bits, and 7. Which of these do I need to use to build up 7? Now here's a good trick for you. 8 is this place value here. 7 is 1 less than this place value. So I will need to use every single one of these place values to make the 7. And that's true for every single binary number. So next would be 16. So 15 would be the combination of all of this. The next one up is 32. So 31 is the combination of all of the place values that are less than 32. Let's get back to our conversion. So I need the 0 here. And remember, this would be +7 in here. So the step 2 is inversion. Again, how do I do this inversion? I copy the number until I copied a 1. So I copy the number and the first digit I'm copying is a 1. So I've already copied a 1. What I need to do next is invert all the rest of the digits. So 1 becomes 0, 1 becomes 0, 0 becomes 1. So this is -7 in 4 bits 2's complement. Why do I know that it's minus? Because this digit here, the first digit, tells me that this is a negative number. Well, it tells rather the computer that it's a negative number. Now let's look at a somewhat different example, because in these 2's complement notation we can also show positive numbers. So let's look at what 3 would look like in 5 bits 2's complement notation. Now step 1 is the conversion part. Now we're using 5 bits, so I need to place the 5 place values. 1, 2, 4, 8, 16. So 1, 2, 3, 4, 5 place values. Then the next thing I need to do, which of these 5 place values I need to use to build up the 3? Well, 3 is 2 plus 1, so the rest of them I'm going to fill in with zeros. But why do I need these zeros? These zeros are vital information. They're telling the computer that this is a 5-bit 2's complement notation. I cannot lose them, because otherwise the computer will not be able to read it. So do I need step 2? Well, actually don't, because step 2 goes for the negative numbers. So I'm converting if there is a negative number. But there is no negative number in here. I have got +3. So when I look at the binary code now, it starts with a 0, so I know that this is a positive number, and the rest of them I can build up the values, and then I can decode that this is positive 3, because 2 plus 1 makes it 3. So whenever you are asked to convert a positive number into any bits 2's complement, it will be very, very simple, because you just need to convert it as ordinary binary number and then fill in the rest of the empty place values with zeros to make sure that you're using the correct length of the bit. So how we can make sense of these 2's complement notation the other way around? So if you see a number 1 0 0 1 1 and you are told that this is a 5 bits 2's complement notation, then how can you convert it back into ordinary binary number? Now the first digit is 1. That's telling you this is a negative number. So this has gone through the kind of inversion process. So we need to reverse that inversion process. So how are we going to do that? Again, the inversion process was copy the number until you copied 1 and then invert everything else. So copy the number, I copied a 1, again the first example was a 1, then I need to invert everything else. So 1 becomes 0, 0 becomes 1, 0 becomes 1, and 1 becomes 0. Now this is the positive equivalent of that negative number. And the next thing that I need to do now is find out what binary number is this. So just put the place values on top of the number. And then this one is 8 plus 4 plus 1, which is 13. So this number here, it's nothing else but negative 13. Now to double check, let's go through the inversion process that we already learned. So I know that this is positive 13, to 0, 1, 1, 0, 1, this is positive 13. So invert it and make it to a negative number. Copy the digits until you copy the 1, that's been done here, and then invert everything else. 0 into 1, 1 into 0, 1 into 0, 0 into 1. And voila, we got back the original number. So this should convince you that yes, this is minus 13. Let's look at another number. So this will be 0 1 0 1 1. Again, this is 5 bits 2's complement. So this is again a 5 bits 2's complement notation, and when we look at the first digit, it tells us that this is a positive number. Every time you see the 0 digit at the front, you should be rejoicing, because it tells you that this is going to be an easy calculation. This is just like any ordinary binary conversions. So this number has not gone through any inversion process, so all you need to do now, put the place values on top of the number and then just add those numbers together. 8 plus 2 plus 1 makes 11, so this number is positive 11 here. There is one very, very common 2's complement notation method, and that is the 8 bits 2's complement. So we're using the 8 bits because with this we have got quite a bit of a variety of showing usefully big numbers, but these numbers are not too big to carry the calculations out by hand. Obviously 8 bits is too small for the computer, so when the computer uses negative numbers, it's using a lot longer than just 8 bits, but the logic and the sequence and the calculations are exactly the same. So let's look at a couple of examples. What would minus 23 look like in 8 bits 2's complement? Now step 1 is convert. So 8 bits, so we need 1 2 4 8 16, that's 1 2 3 4 5 32 64, 1 2 3 4 5 6 7, and we need one more. So we need all of the 8 bits. Now that kind of shows you the first bit obviously will be used for the sign, so that is not a place value, because that's been reserved for the sign, either positive or negative. But it kind of tells you that you can work with quite nice big numbers, because remember, this is 128, So the rest of them makes up 127. So you can use up quite big numbers in here, positive and negative, with 8 bits notation. So which one of these do I need to use to make up 23? Now 16 is the biggest that I can take out from here because 32 is too big. Now what's the difference between 23 and 16? Well, that's a nice and easy 7. And then 7 is the combination of 4, 2 and 1. Now here comes the trick, because it's an 8 bits notation, I need to place 3 zeros here at the front. Okay, so that was the conversion part. Then comes step 2, we need to invert. So when we're inverting, we copy the number until we copy the 1. So we're going to copy the number. First digit is 1 again, so I already copied the 1. So I need to invert everything else following on. 1 becomes a 0, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0, 0 becomes 1, 0 becomes 1, 0 becomes 1. And sorry about the wonkiness of it, but this number is the 8 bits 2's complement equivalent of minus 23. Let's do one more example of the 8 bits complement, 8 bits 2's complement. Okay, let's do a negative number, because positives are quite easy, so it doesn't need too much calculation. Let's do something like minus 80. Okay, again, step 1, we just need to convert it. Again, use the place values. 1, 2, 4, 8, 16, 32, 64, 128. Again, I can quickly and easily build up this place value table by starting with a 1 and keep doubling as I'm going from one to the next. Now, the difficult bit here is making up minus 80. Now, 128 is too big, and besides, if you get to a number that is bigger than 128, you run out of bits, so you would need more than 8 bits to represent that. You can always extend your bits longer than 8, but if you are in 8 bits and you are asked to do something bigger than 128, then you won't be able to do that, so be aware of that restriction. So 80, the biggest place value is 64 that I can use up. So what's the difference between 80 and 64? That is 16. That's quite useful because 16 is here. So the rest of them, including the 128, need to be filled up with zeros. So that is the positive 80. And then comes next step, we need to invert. Now, I wanted to show you an example like this because all of the previous examples we started with a 1 straight away, and then we could convert everything else. But the rule says that copy the number until you copied a 1. So with this number, I need to keep copying the zeros, all 4 of them, until I copy the 1. Okay, so this part of the negative equivalent of the this part of the negative 80 will be the same as the positive 80. And then what I need to do, once I copied the 1, I'm going to invert the rest of them. So in this number, I'm only inverting 3 of those digits. 0 becomes 1, 1 becomes 0, and 0 becomes 1. And that's really handy because, again, the first bit in here is a 1, so that tells me that this is a negative number, and I'm happy about that because I wanted to show minus 80, and the rest of them are just a notation for the computer to say that this is actually minus 80. Now, I hope that you understand the 8 bits 2's complement notation better now. I encourage that you do the following practice questions, and you will find the answers later on. For this video, we will have 2 sets of questions. Here are the first set. This is the answer to the first set. Here is the second set. And here are the answers to the second set.